I want to start this lesson with a bit of panic. These are class 3 problems, so I say, ah! Here we've got a building, and there's this other building. Look, it's got a green roof. And the building's over here, and Ben Colleen, having done something that he shouldn't have done, is going to jump to the other building. He says the separation of the two buildings is 4 meters. Wait, you haven't read the problem. Here's the problem. Ben Colleen jumps from the top of one building 4 meters away to another building. He leaps with a velocity of 5.0 meters per second above the flat roof. Will he make it to the top of the other building, which is 2.5 meters shorter? That's the question. So here's what I'm about to do. I'm about to draw you a little sketch of the building, and Ben Colleen's up here, and he's running, and he jumps. And he's gonna jump, and his path is probably gonna be something like this. Whoa! In which case he would be okay, or he's not going fast enough, and it's gonna be like that. I don't know, but let's figure that out. I do know that this distance right here is 2.5 meters. That's the difference in height between one building and the other building. So this is not an obvious problem, and we don't know really everything that's going on, but let me show you what we can do with this problem. There are 2 ways to approach it. One of them is, if we're trying to figure out if he's going to be alive, one of them is to figure out, for instance, how far over he is once he has gotten down by 2.5 meters. Now, that approach is not the one that we'll follow, but I just want to show you what you could do. You could say delta y equals negative 2.5 meters. Now, you need to figure out why I said it was negative, because I'm not going to waste my time talking about that. Be very careful. And you could say that the acceleration in the y direction is negative 9.81 meters per second squared. And you could say that the initial velocity in the y direction, oh, could you? What is the initial velocity in the y direction? Before we even begin this problem, we need to draw his initial velocity vector. And this velocity is the full speed, 5.0 meters per second. If we resolve this, though, we're going to be talking about the x component, which is v naught comma x, and the y component, v naught comma y. This is just v naught times the cosine of theta. This is v naught times the sine of theta. Let's get some numbers on those suckers. I'm talking about 5 times the sine of 15 degrees, and I'm talking about 5 times the cosine of 15 degrees. I enter those 2 numbers in my calculator, and I find these 2 numbers. Velocity in the x direction, 4.8296 meters per second. And the velocity in the y direction, check that out, that is 1.2941 meters per second. Okay, so the initial velocity in the y direction is given over here as 1.2941 meters per second. Now, this method says we know all of that stuff, and we're trying to find delta x at that time. And if he's gone 4 meters by the time he's fallen down, well, you see what I mean? If he's fallen down 2.5 meters and he's only gone 3.5 meters, that means he's on this path right here, which means it is not going to be a fun end. But if he's gone 4 meters, or let's say he's gone 4.5 meters, horizontally, when he's getting to negative 2.5 meters in y, then he will be okay. Now this is not a good way to do it, and I'll tell you why. In order to find delta x, we need an equation in x, and there's only one. It says delta x is the, wow, this is tropical violet? Wow. It says delta x is the initial velocity in the x direction times delta t, and we don't know delta t. So now we're on a side quest to find out how long it takes for this to happen. And if I'm looking at my kinematic equations, oh, I'll go get them. They're over here. Kinematic equations, where are you? So I'm talking about initial velocity in the y direction, and acceleration in the y direction, and delta y, and time. Initial velocity, acceleration, delta y, and time. Initial velocity, oh, not this one. Oh, not that one, because we don't have delta y. This one, okay, the classic. So write the classic down, I'll tell you, delta y equals the initial velocity in the y direction times time plus 1/2 the acceleration in the y direction times time, sucker, square. And we're trying to find time, and we know all of this stuff. We know that and that and that. We have a quadratic equation. Personally, I say at that. Because the quadratic equation is a lovely thing if you know how to work it, but almost none of my students actually know how to work it. They can tell you what it is, but they can't take an equation right here and get t. T equals, question mark, question mark, question mark. So that's a challenge to you. If you want to do it the quadratic equation way, by all means, do it the quadratic equation way. But I'm proposing a different way to solve this problem. And that is really just a difference in perspective. What I want to do is I want to draw myself a little picture of the roof and the green roof. And Ben Colleen again. And Ben Colleen is jumping right here. Here he is. He's a purple guy. Jumping. And I'm going to ask, instead of the question, let's see what we asked over here. The question that we asked over here is, how far has he gone to the right when his delta y is negative 2.5 meters? I'm going to ask the exact inverse question. I'm going to ask, how far up or down is he once he goes 4 meters in x? Okay, that's our challenge. I know that if he leaves with a velocity in the x direction, he will ultimately go 4 meters in x. That's the plan. If, though, if delta y is greater than negative 2.5 meters, then he lives. If delta y is less than negative 2.5 meters, this will not be very much fun for him. There's a trampoline down at the bottom, so he's going to be okay. It's actually going to be a lot of fun. If he misses, it's going to be a lot of fun. But we'll still call it squishy trampoline, at least. There's a kitten on the trampoline. So he doesn't want to land down there, but he's going to be fine. So here's the thing. I'm saying that Ben will make it to this plane. He will cross that plane at some time, and I just want to know when that's going to happen. And I'm thinking about the x direction to do that. In fact, I know delta x now is 4.0 meters, and I know the initial velocity in the x direction. That initial velocity in the x direction, if you don't recall, is 4.8296 meters per second. And I also am trying to find the time. So delta t is going to be delta x divided by the initial velocity in the x direction. So the time at which that happens, the time at which he gets to right here is very simple. It is just 4 divided by 4.8296, and I get a number. It says 0.8282 seconds. That's how long it takes for Ben to get to this plane right here. And now I need to ask the question, how high up is he? So I'll do that. And the answer to the question, how high up is Ben Colleen, can be answered with this one, certainly, but we don't know Vy. This one, the classic. Right, let's go to the classic again, and I'm just going to plug in that time right there. The time is 0.8282 seconds, and I get delta y equals the initial velocity in the y direction times time plus 1/2 the acceleration in the y direction times time square, and I plug in that time. Should I write this out for you? Okay, I'll write it out for you. Initial velocity in the y direction is 1.2941 meters per second, and then I'm supposed to multiply that by the time, which is 0.8282 seconds. That'll have units of meters, that's good. Plus 1/2, oh, I'm going to need more room. Acceleration in the y direction is negative 9.81 meters per second squared, multiplied by that time. Here we go, multiplying by the time squared, 0.8282 seconds squared. If I type this into my calculator, I will find out how high up he is. This is a life or death question. 1.2941 times 0.8282 plus 0.5 times negative 9.81 times 0.8282 square equals, it's negative 2.3. What does that mean? That is where Ben Colleen is in height when he gets to this plane right here. And it seems to me like negative 2.3 is greater than negative 2.5, so he's going to be fine. Yay! And he's gonna jump, and his path is probably gonna be something like this. Whoa! In which case he would be okay, or he's not going fast enough and it's gonna be like that. I don't know, but let's figure that out. I do know that this distance right here is 2.5 meters. That's the difference. Will he make it to the top of the other building, which is 2.5 meters shorter? That's the question. So here's what I'm about to do. I'm about to draw you a little sketch of the building, and Ben Colleen's up here, and he's running, and he jumps. I want to start this lesson with a bit of panic. These are class 3 problems, so I say, ah! Here we've got a building, and there's this other building. Look, it's got a green roof. And the building's over here, and Ben Colleen, having done something that he shouldn't have done, height between one building and the other building. So this is not an obvious problem, and we don't know really everything that's going on, but let me show you what we can do with this problem. There are 2 ways to approach it. One of them is, if we're trying to figure out if he's going to be alive, is going to jump to the other building. He says the separation of the 2 buildings is 4 meters. Wait, you haven't read the problem. Here's the problem. Ben Colleen jumps from the top of one building 4 meters away to another building. He leaps with a velocity of 5.0 meters per second above the flat roof.